Welcome everyone. Thank you so much for the opportunity. Today my presentation is about capillary rise in water setup, which causes pressure changes in hysteresis. And the way that we examine this is by doing experiments and numerical simulations. And also we try to verify this with analytical solutions. And as Martin said, I'm Nepal, I'm a PhD student supervised by Marco and Juan, also in collaboration with Georgie at UB and Ivan at NFM. So why do we care? Why do we choose this topic? Is because it's so prevalent in many two-phase fluid displacement problems, like geological CO2 sequestration, underground hydrogen storage, and many others. And what exactly is pressure changes in hysteresis is depicted in this right diagram, which shows pressure in y-axis and saturation in x-axis. When we see these two lines, green lines and orange lines, these two lines are different, of course, because the green line is for primary imbibition or just imbibition, and brown line is for drainage. And we see clearly there is some hysteresis going on. And that's because of intrinsic heterogeneity in our medium. Whenever a fluid tries to invade into the system, in this case porous medium, in this case, I mean the figure that we're looking at, the fluid experiences increasing capillary forces that causes sudden jump, which is also known as Haines jump. And during the same drainage process, this fluid will get entrapped in this smaller pores that causes this pressure sensitive hysteresis. And we're examining this behavior. And why do we choose water in our problem? It's because it's a simple setup, it's not complicated as in porous medium, and it resembles a single pore throat, as we see in porous medium. And I think one of the most important reasons that which is important was to also be able to derive analytical solution. Because it's easy, as we shall see in upcoming slides. An ink bottle is really a tube which has a constriction somewhere in the tube, and that constriction can vary, steeper constriction or less steeper constriction, and then we change this gradient in our investigation.
Yeah, do you mind if I would ask you?
Oh yeah, absolutely.
So this arc tangent gradient, did you choose it because it has a smooth shape, I guess?
You mean this?
Yeah, so the arc tangent, I guess, is because of the smoothness properties.
Not really, no. So this is just a definition of a gradient. So A here is the change in diameter of radius of
okay, I see. Sorry, I see.
And H is the height, right? So it's just a definition of gradient. The objective is to investigate this origin of pressure sensitive hysteresis in an inverted setup. That's the only objective that we have. And how do we do it? Like I said, we do simulation, we do experiments, we also try to verify with analytical solution. Let's go into simulation. We need some set of equations to solve. And the equation that we solve is continuity equation and momentum balance equation. We consider fluid to be incompressible, isothermal, immiscible, and we solve this equation in a numerical solver. So the term that I want to highlight here is FST, which is surface tension force. And surface tension force is nothing else than, of course, the coefficient, surface tension coefficient, K, curvature, and N delta T, this gives us the direction. N is normal, unit normal. And delta T is it's a derived delta function which only gets activated when the solver when there is interface. When there is not interface, this FST term will be zero because of course surface tension is only present when we have a surface. If not, then this GT term will be zero. Like I said, the way that we solve these equations is in numerical simulator called OpenFOAM. We use interFOAM solver, and we use volume of fluid method to differentiate two different phases. And volume of fluid as you may know, as you may not know, just I'll briefly describe what it is. It's a way to solve our governing equations and way to add two phrases in our equation. The way that volume of fluid works is we have this scalar function called alpha, you can name it any name. And let's suppose if this is our grid that we discretize, we assign a value which can range from 0 to 1. If it's 0, then it's air. If it's 1, then it's fluid or water, whatever. And all these intermediate values where our interface is. We calculate this FST term by a method proposed by Bradfield. It's also called a continuum surface force model. And the fluid properties are calculated depending on this alpha value. So we kind of average all the alpha in all the cells and multiply. So this 0.4 would then multiply with the density of the fluid plus 0.2. So it goes on like that with density and with viscosity. And this volume fraction term is then advected. So next time we advect this volume fraction term. And
so these blocks over there on the right is your grid, or
yeah, it's just
so every number is an element.
The numbers that we see there is
The boxes
alpha
of this
value.
number is
Alpha values.
okay.
And do the values in the diagonals, because if you do the diagonals from left to right, they have the same values, they have to be necessarily the same.
You're very
Yeah, you can take any number. I mean, we shall see some problems with this volume of fluid method. So here, I would like to stress a bit more to this term, which we add, because these two terms are just standard advection terms. But the third term that we add is to compress the interface so that it doesn't go like berserk. We try to minimize the thickness of the interface. We don't want our interface to be so thick that it's not physical anymore. So this term will try to compress the.
Okay, you only solve once the momentum equation, the divergence-free equation.
Exactly, yeah.
So one for the liquid and one for the other.
Exactly. So this is the beauty of volume of fluid. So beauty, whatever you want. So yeah, exactly. Volume of fluid method will allow us to solve just one set of governing equations. We don't need to solve for water and for just solve one equation.
So it's like this interface compression term is kind of like a logistics term, right?
Yeah. All right. So once we got our numerical solver, we wanted to verify the numerical solver, and we did a very basic solver validation problem. It's a straight tube. It's a capillary tube which has a size of 1 millimeter in x direction and 20 millimeters in y direction. We set our boundary condition: pressure inlet, pressure outlet, walls is no slip. And we use a fluid, it's 10 times as viscous as water and has almost around 3, so surface tension of water would be 3 times as surface tension of this fluid that we are using. So just to briefly give you an idea, we are using. So this fluid is also known as silicon oil, rhodocylindric Haines lane. And what we see in this plot is in x-axis we have time, y-axis we have time. So we try to plot the evolution of this liquid rises just because of capillary force. And here we observe that at some point, after 1 second, it kind of plateaus and it converges. This dotted line. This dotted line is analytical solution from analytical solution. And what we observe, the convergence error from our numerical solver was around 1.95. This can be attributed to I mean, there are many reasons. One could be grid size to pores. The other problem probably is the most important problem is, and I don't want to go into that part, is because of spurious currents that arises at the. So anyway, after we verify our numerical solver,
Sorry, why the analytical solution is flat, but then change with.
yeah, it's just a steady state solution. So it's just what would be the height of the interface. So this solution will only give the final height.
The steady state solution.
I think the problem you focus on is the transient problem, and I think the transient simulation is also simple. And the analytical solution for transient capillary rise is linearly proportional to square of time.
Yeah.
So why
At the beginning.
So why not in this case?
I'm not interested in dynamic part. I'm only interested in what will happen at the quasi-static limit. I'll talk a bit more about what exactly is quasi-static. Maybe that will clear up the conclusion.
Thank you. And another question, you see that the fluid is water, but I remember the surface tension for water is water air.
Fluid is not here. Fluid is silicon oil.
Oh, okay.
Where do you see it?
Yes,
Waiting fluid is silicon oil.
Sorry.
Yeah, that's what I said. This fluid is 10 times more viscous than water,
Okay.
but has 3 times less
Yes.
surface tension than water. So,
Um,
so after we verify our numerical solver, we then set up our problem. We are interested in doing cyclic imbibition and drainage. We do numerical simulation in many different capillary tubes with varying cross-section gradients. What does it mean is we only vary this thing. We only vary the gradient. So we start with a very sort of flat tube, and then we gradually increase the gradient. And again, the fluid property is the same as we discussed earlier. And the numerical simulation is done quasi-statically. And if you guys don't already know what quasi-static means, is we increase the pressure at the inlet. We let the fluid to rise to equilibrium height. We increase again. And we do this stepwise. We will only increase the pressure once fluid has stabilized. And that approach is quasi-static. All right. So this coming to experiments, this is a schematic diagram of experimental setup. Here we have capillary tube. So the capillary tube, silicon oil is fed at the bottom, and this is then connected to this reservoir, which has silicon oil. It's then clamped to this platform, which can be raised and lower. And this is pressure gauge where we measure our pressure. It's very simple. And then we capture from camera, we process it completely. This is a laboratory setup. Again, here, this doesn't look very good, but this is where our capillary tube is. Camera is here. And we use same fluid that we've been using up to now, but the only difference in experimental setup is the contact angle is 0 degrees. So the contact angle in the fluid that we are using, as you may remember, so this is 45 degrees. But in experiments, it was 0 degrees. And this I didn't know. I run my simulation with 45 degrees, but then when I started my experiment, it was 0 degrees. So this was on the difference. So anyway, so this is the bottom that we have, the experimental setup. And this, as you can see, it's a cube. And the way that we sort of make this capillary tube is by drilling. We drill, and then we change the drill bit so that it decreases the diameter, and That's how we do it. It's a very simplistic method. All right. So we have discussed simulation, we have discussed experiments. Now let's go into analytical solution. So analytical solution we try to derive is to calculate the height, also known as drilling height. Maybe I should have talked a bit more about drilling height. Yeah, so drilling height is the equilibrium height. So once you set your boundary condition, once you put pressure at the inlet, the fluid that will rise, the height that it will attain will be the drilling height. And we are interested in calculating this drilling height. And the way that we do it is by force balance. It's very simple. Capillary force, which is acting upward, say if we consider upward force to be positive, capillary force to be positive, gravitational force of fluid which is dragging it downward will be negative, external force, because we are applying pressure at the inlet, will be positive, and this minus forces from the walls would be the forces from these guys. So these walls, which are slant, will also then we'll also have a reaction force that is pointing, or reaction force which will be pointing perpendicular to the walls. But then this reaction force will have a vertical component that is directly directed towards negative y-axis. And we do this by dividing this tube into 3 sections, as we shall see in our slides. So coming to this first section, which is, so with H is Joules's height again. When Joules's height is between 0 and H1, that means in this rectangular box that we said, we calculate capillary force, we calculate gravitational force, we calculate external force, but we don't calculate forces from the walls because fluid has not reached this region yet. And we do this simple math, we arrive to this calculation. It's pretty straightforward. We go to next zone. Now we are in this zone, and this gets a bit more messy, and I try to make it more simpler by excluding some derivations. But anyway, so the extra term that we have is this vertical component of the wall forces.
So this doesn't depend on R2 at all.
Not yet, because we have not yet reached R2 yet. So R2 is the radius of small tube, because we are still within the lower limit. So it doesn't yet depend on R2. We'll come to that. So we calculate surface tension force. The slight modification that we see here is, so cos contact angle now is not theta, is theta minus alpha. So here you may remember it was just theta, but here is now theta minus alpha because it changes as the interface into this constricted region, the contact angle changes. And then we should sort of modify these forces. So anyway, so if we plug in these forces into our equation, we arrive to this, not very good equation, but yeah, so this basically means, I don't know what this really means, but so this has dependence on alpha, so how,
you see that theta was the contact angle.
Theta is contact angle, yes, fluid contact angle, and alpha is the gradient of the tube. And yeah, exactly. So R1 is the radius of bigger tube, R2 is the radius of smaller tube, H1 is height up to this beginning of conical section, and H2 is the end of conical section. And H will be, small h will be the height of the interface. All right. And going into third zone, so here, now we are in this region, we again calculate all of these 4 forces. We get this equation. And this equation, if we look closely to each component, we see that the first term is just capillary forces by small g. So R2 sigma cos theta. And P pi R1 square would be the external force that is applied. and this guy, pi R1 is for H. So it looks as if the fluid was, the tube was not, the diameter did not really change. It looks as if, so this surface tension force is actually holding only this small amount of fluid. But this guy has not only that fluid, but also the downward component of these wall forces, which then, balance of this capillary forces that is acting on this smaller wall. And this is also known as hydrostatic paradox. And by simplifying this equation and solving for H, we arrive to this formula for zero inside. All right, so now that we discussed how we arrived, or what were the methodologies, let's look at the research section. And this is divided into simulation and experimental. And simulation, we ran simulation for, here we see 1, 2, 3, 4, 5 different tubes. So we ran simulation in 5 different tubes with 5 different cross-section gradient. We plot pressure over silicon oil content. So this is the volume of fluid that is in this tube. And we saw how it evolves with varying pressure. What we see in this Zoom diagram is blue line has a bigger loop. And why is that? Is because the blue line has greater gradient. It's more steep. And once we decrease the cross-section gradient, this loop gets smaller, smaller, and smaller, and at some point it just disappears. So what we can see here is, if we have steeper cross-section gradient, we have larger hysteresis. If you have less, and vice versa, of course. And figure to the right, x-axis is gradient, y-axis is area under the curve. What does it mean? We calculated the area under this hysteresis loop for each gradient and try to plot it. So what we observe is, of course, for higher gradient, we have larger area. Larger area meaning larger hysteresis loop. But as we decrease our gradient, this area starts to decrease. And it decreases quite precipitously, and it goes to almost flat. And here, at 0 degrees, we expected it to be 0, because if the tube is straight, there should not be any hysteresis. It should go up and down, that's it. There should be no hysteresis. But still, we observe some hysteresis in our numerical simulations. And again, this could be of many different reasons, but here I termed it as numerical hysteresis. And the sort of conclusion from this plot is, steeper the cross-section gradient, more pronounced in the places as the hysteresis. And these are some experimental results during imbibition. So what we can see here is, maybe this will get more interesting if we compare these two images. So this first slide is for imbibition. The second slide is for draining. So what we observe is, so we start our simulation at pressure equals to 0 millimeters. We at 4 it enters the tube, but still is at the constriction. At 4.5 still at the constriction. At 5.5 still at the constriction. At 6 it jumps. And it just goes linearly up to 9 millimeters. But so this at 4.5, it was still in this constricted region. During drainage, 4.5 was here. That means we have 2 different saturation values for the same given pressure. That means we have some hysteresis. And we predicted this because, of course, there is a change in cross-section gradient, and this should, of course, induce some hysteresis. But this is quite clear that at 4.5 we are here, at 4.5 we are way above. And only at 4 we actually reach this point. So this is just to show you experimental results showing pressure saturation hysteresis. And coming to plot, so these are images. Right? And what I did with these images was I extracted the interface side from these images, and I tried to plot pressure saturation for different experimental tubes. So far I have just two. So I did experiments on 3. There was problem with 1, and so the result here is pressure saturation curve for 2 tubes, for 2 capillary tubes. And this blue line is for 12.95 degrees, and orange line is for 15. And we can also see from here is as we increase our gradient, the hysteresis gets bigger. All right, wrapping up the presentation, what we observe is steeper the gradient, more pronounced is pressure saturation hysteresis. We observe this from numerical simulation and with experimental methods. During imbibition, interface experiences a sudden jump at the entrance of the constriction, and this is because the contact angle changes from theta to theta minus alpha. So as soon as it reaches this part, so if my interface is here, slight disturbance in external pressure will induce the interface to change its contact angle from theta to theta minus alpha, because as soon as the interface touches this region, the contact angle changes, and this change in contact angle causes infinitesimal difference in pressure at the inlet, causes the fluid to rise at the entrance of the constriction. And we also derive analytical solution for pressure sensitive trajectories. And before I conclude, I have to admit that this analytical solution I wanted to put into this slide, but there were some problems, and we discussed this with Juan and with Marco. So I couldn't really put it here, and the plan was to compare all these results together. So the numerical simulation, experiments, and analytical solution, and try to sort of verify all these results. But at this moment, I couldn't do it with analytical solution, but hopefully that's the plan. Thank you. Thank you very much. Yeah, any questions?
Yeah, thanks for your presentation. So is there an explanation why, so in this graph where you compare the steady state constant solution and the numerical solution, is there an explanation for why, I think it was after 1 second, it reached the asymptotic limit like very fast, and then it remains like almost constant. So is there an explanation for this high non-linearity in the numerical solver?
Actually, we do expect this non-linearity in our physical experiments as well. When you do experiments on this setup, you will also see it starts to rise gradually, and after some point, it just stops rising. So we also see this non-linearity behavior in the real world. But in numerical simulation, this non-linearity is not really captured properly by numerical solvers. I mean, if we use one solver over the other, the graph changes completely. But what we are really interested in this study was, would it be able to predict the final equilibrium height? And some solvers really predicted well, like the solvers that I'm using. It has almost 3% error. But this really depends. I mean, the one solver that I was using before was sharp surface force model, which was really good in predicting the Jordan height, but it was terrible during transition because it had a equation which then dampens the oscillations which we see in capillary rise, and sometimes it can be desirable, sometimes it cannot be desirable. So it really depends on something.
Okay, thanks.
Thanks very much. Just one thing for geology before I ask you the question. So when you use a blazing solver, you don't have to do a physical solve of how you get from to the medium, but often the blazing solvers somehow more or less solve the physics. because that's like these, or something similar. So that's why, I should say that often you see something that is similar to the derived. But it doesn't have to be this way, but it turns out to be right. Now the action. So, I'm sorry if I missed it, but in the plots you showed of the experimental results, you didn't have the numerics on top, is it? Can you go to the slide? There. Yeah. So this is experimental, I'm just yes. But the numerics are not there.
Yeah, you could do a comparison with them.
That's the plan. I mean, you can see so this is not really hard. This is high pixels. So I'm cheating over here because
Wow,
I have to
just very scary, right?
yeah, I have to raise the of those one.
But you have not tried. I mean, I understand you don't have the analytics quite working yet,
Yeah, exactly.
but you could check this numerically,
Right.
Or
Yeah.
is that a problem?
Yeah. So the plan is to compare these experimental results to try to verify this with analytical.
Yeah.
Yeah, exactly.
But I mean, like for now, while we don't have the analytics, you can compare directly to the numerics, yes?
Correct.
Yeah. So that, I think that would be what we.
Yeah, exactly. Yeah, the slight problem, I mean, yeah, you raised a good point. So this is 3D, of course, experiments are 3D. And in numerical simulation, the results that I showed was 2D. And so there was, and
There is a factor of 2 in the circumstantial.
yeah,
But this is this is-
yeah, I mean, I have to do it.
You could just have a 2D simulation and fake the circumstantial. Would that work?
I tried to fake it once.
It didn't work. We can discuss it. But okay, I see that.
But
What I'm saying is to fudge the circumstantial in the development place so that you have the extra factor of.
yeah, you can predict the height. Yeah, so
Prediction of the plates. And if you compare that to a 2D simulation.
yeah, exactly.
But like you have to do a radial thing. So I don't know.
We try to do a simulation to make the symmetry.
Because it's 2D Swiss, is a
Exactly. So that there will be.
You can have a 2D.
Because in principle it's good.
Depends on the code.
I understand it, but I don't think actually resolve the problem. I think solving the would be problem. The radial direction, because everything else is symmetric. We can talk about it.
Yeah, sure.
Because this 2D model is 2D cylindrical, or is it just 2D?
Exactly. So it's like a pattern plane person.
It's 2 plates, exactly.
Yeah, that's what.
But you cannot go into a 2D cylindrical model.
The plan is to 2D cylindrical.
The cylindrical coordinates or something.
Radial storage.
Yeah, radial symmetry. It is a possibility. Maybe it is a possibility.
Maybe, yeah, that's a good point. But then maybe I have to change my equations to, because
Yeah, maybe.
yeah, it's a bit complicated because I'm using OpenFOAM and I'm not, I mean, I do some minor solver changes, but I'm not really expert in changing labels, so maybe.
You like it?
It's nice work on the classic ink bottle problem. I just wonder if you can comment on taking this work that you're doing eventually and thinking again about the real world of messy, complex bundles of heterogeneous pores. What's your long-term hope for translating this work back to?
Yeah, exactly. So the plan is to actually we wanted to do on porous media first, then it got complicated. And like I said, then it chose this important problem. But the plan is to do similar experiments and numerical solve the situation. in porous media. With drainage.
Scans of real pores, or like with like glass spheres, or what's your?
You mean scans from the rock? Yeah. Just a random distribution of pores into a given domain, and then try to discretize it, and use numerical simulations and do experiments. Maybe not analytical solution because it's
So what would you expect by looking at these curves? What would be the expected result if I now consider a fluid with a higher, lower surface tension? What is the role of surface tension in these blocks now?
very interesting one, very good point actually. So if we look at this analytical solution, this solution, if we increase sigma, we expect higher edge. I mean, it's not, maybe it's not very apparent here, but it's a little high. So in principle, if we increase sigma, this rise will be even higher.
All right.
So it will go even higher. So in principle, the hysteresis loop should increase.
So in the case of a lubricant, for example, we shouldn't expect hysteresis
In case of lubricant,
of a lubricant, no, or something that has no surface interaction with the container.
if there is no surface tension, then there is no hysteresis. Because
There's no capillary rise.
this is all about capillary rise.
This graph of the slopes, apart from the cycles, the slopes on the left and on the right shouldn't be, I mean, maybe they are, maybe it's there. They should be of the same slope, right?
This guy?
Yeah. No. After
This unit.
this and the other one. This. And maybe they are parallel, I don't know. But the first ones are not. I don't know.
Oh, we can examine this with an ideal solution. So this is essentially the third part, right? So what's changing here? R2 is same, and in that case R2 was same, R1 was same, sigma was same, theta of course is same, so it should be same. The gradient should be same.
And is it the case in the result? I may be misled by my. Seems a bit off, no?
Yeah,
That's what the initial at least. I don't know. Maybe not. Now I'm not sure why it did.
Would say more or less the same.
Yeah, maybe not. I don't know.
Perfect level.
But the initial one is a bit.
Yeah, initial one, I don't know. It's really true.
I'm sorry.
No.
Hi, I'm Rich. So thank you for talk. It was very good. I do some problems. First of all, you mentioned that the Haines jump and capillary hysteresis in porous media. I think the hysteresis in porous media, especially for two-phase displacement, it involves the interactions of multiples. So
Interaction
interaction between multiples, for example, pore-to-pore physics. For example, in drilling, the Haines jump breaks through into close to the neck. So the interface in other multiples will retract and refill the.
Yeah, exactly.
So this process involves the interaction between pore-to-pore and multiples. So do you have any plan to upstream this analysis?
Yeah, exactly. Like I said, the plan was to do this study with porous media.
Yeah. And
Now, after I finish this, the plan is to do similar investigative study with porous media.
okay.
With multiple pores, interconnected pores, of course. And like I said, when one pores drives the fluid upward, it might suck fluid from the other field pores. And
Yes. So do you have a good choice for upscaling tool? Maybe planet models are good. And our group has, sorry, so our group, in here has very similar at the, my colleague studies the two-phase displacement in convergent divergent structure that we say convergent divergent pore-scale or structure.
I have no idea what,
Yeah.
what we can.
And they modify the equivalent contact angle to convert, to consider, to take account the structure effect, and they could,
Okay.
so they modify the equivalent contact angle, and it goes, the contact angle changes with the two radius. And then they use Fortnite model to carry out upstream analysis.
I mean, in our problem as well, we modify contact angle. If you look into derivation, like I said, so here the contact angle was determined.
Because you're right. So another question is there necessary to consider the gravity?
We have gravity here.
So is it necessary to consider the
Gravity.
Yeah. I think gravity is not responsible for hysteresis.
It has an effect on the flow and how high it goes.
I mean, if we don't have gravity, then there is nothing holding the fluid to overflow. It just keeps on going and going and going. And we want to stop the fluid to do that. And gravity does that for us in this case.
And the last question is that usually you have done some work on analytical solution, simulation, and experiment. So is there a cross comparison between these two parts?
Yeah, of course, yeah. That's the optimum.
Okay. Thank you.
Okay. Someone else? No, thank you for your presentation.